Good evening, Engineer Gumapak. I am Ria Luisa C. Cabalano, one of your students in numerical method, and this is my Module 2 machine program. What is C++? C++ is a high-performance cross-platform language developed by Bajarna Strauss Group as an extension of C. It provides programmers with a high level of control over system resources and memory, and it has evolved through five major updates since 2011, including C++20 and C++23. As one of the most popular language globally, C++ is essential for operating system, GUIs, and embedded system. Its object-oriented structure allows for clear organization and code reuse, which helps reduce development costs. Additionally, its portability ensures that applications can be easily adapted for multiple platforms. While C++ shares much of its syntax with C, the main difference is that C++ supports classes and objects because it is closely related to C, C Sharp, and Java. It is relatively easy for programmers to transition between these languages, making the learning process both practical and rewarding. Here's my chosen topic, which is the topic for point one, the Newton-Raphson. So the Newton-Raphson method is a smart way to find the exact root of an equation by using geometry. It starts by making a guess and drawing a tangent line at that point, which acts like a slope showing the direction towards the root. By using the slope, the formula x sub 1 is equals to x sub 0 minus f to the power of f times x sub 0 over f prime x sub 0 calculates a new, more accurate guess. So this process repeats over and over, quickly sliding down the curve until it reaches the true solution where the value is 0. Okay, next is the example of the Newton-Raphson method for the polynomial equation, and this one is for the trigonometric equation. So let's watch the video of my coding where the user only needs to input the equation or given values and the program will compute the solution. Okay. So as you can see here, this is the header files which has pre-built-in tools like mathematical calculations for mathematical calculations. So this part defines the operation order. Next is the function that evaluates trigonometric functions or trigonometric equations at a sine, cosine, and L. So this one is the main function which is as a control center of my program. So it uses a loop so that my program stays open, allowing you to run multiple calculations until you decide to exit. Okay, I will explain the Newton-Raphson. So Newton-Raphson's function, that's the Newton-Raphson functions. And this part is the iteration table. Next is this part is the derivative formula or formula for derivation. And this one is the formula for Newton's Raphson. This part is the table for output. Okay, let's run the code. You need to type 0 for the topic 4 and type 0 for the Newton's Raphson. So type the equation x cubed minus 4x squared plus x minus 10. Initial guess is 1. So as you can see, this is the iteration table. The approximate root found is 4.80691 and the total iteration is 18. We need to continue because we need to check the trigonometric equation, which is the e to the power of x plus s. As you can see here, exp times x is equals to e to the power of x. So this is the iteration table. The approximate root found is equals to negative 0.56714, and the total iteration is 5. Okay. Next is the Gauss-Jacobi method, the 4.2. So the steps are rearrange the order of equations in a manner that the dominant coefficients for each unknown variable lies in the main diagonal of the system of linear equation. Obtain the iterative formula for each variable by transposing the dominant variable and dividing the equation by the dominant coefficient. Lastly, begin the iteration by substituting initial values to the variables and obtain the new values. So the process is repeated by substituting the variables on the next iteration until the terminating condition is satisfied. No. Since all variables are within a linear equation, then all variables must satisfy the terminating condition. Otherwise, continue the iteration. Okay, as you can see, this is the example for our Gauss-Jacobi method. And let's try to find this answer using the code and let's watch the video. So as you can see, this is the Gauss-Jacobi function. And this part is the augmented matrix where the user will input the value. This part is the initial guesses. This part is the printing the output or which, and this part is the loop for the Gauss-Jacobi solution. Yes, the loop for the Jacobi equation to provide correct answer. Okay, let's run the code and check if the answer is correct. So we need to enter the choice 0 for topic 4 and 1 for Gauss-Jacobi. So we need to enter the augmented value. Okay, as you can see, this is the table. It had a perfect convergence which at k is equal to 13 or iteration equal to 13. And the final converged values, the x1, x2, and x3, which is the x1 is equals to 2.42548, x2 is 3.57301, and x3 is equals to 1.92595. Okay, let's proceed to the Newton's interpolation or the topic 4.3. As you can see, its general form is this one, where the first finite divided difference is this one, second finite divided difference is this one, the third finite divided difference is this one, and the last one is this one. So the first, the second, the third, and the fourth, this one. No, arrange x in increasing order, not in decreasing order, okay? So this is the example of Newton's interpolation. As you can see, it has a value of 2.5 for the x. And let's watch the video if the answer is correct for the following data. So as you can see, this is the function of Newton interpolation. This is where the data is being collected, the data that the user inputted or given. This is the formula for the interpolation. And let's check if the code is correct. Type 0 and type 2 for the Newton's interpolation. So we need to input the number of data points. So you can see here, and the 4 data. So you can see here, this is the divided difference table. And we need to put the value of interpolated or the x. So interpolated value at x at 2.5 is 5.625. The topic 5, the trapezoidal plus Romberg integration. What is Romberg integration? So Romberg integration is a powerful numerical method used to estimate the definite integral of a function by refining the results of the trapezoidal rule. It works by applying a technique called Richardson extrapolation to a sequence of trapezoidal estimates with increasingly smaller step sizes. By combining these estimates into a triangular table, the method systematically cancels out lower order error terms, allowing you to achieve extremely high precision with significantly fewer calculations than using the standard trapezoidal rule alone. So as you can see here in below, this is the rule for trapezoidal rule. And this is the formula for trapezoidal rule and formula for the Romberg. So this is the visual Romberg table. This is the sample problem. 1 over x and the limit is 1 and 2 for polynomial, and this is for trigonometric. Okay, let's watch the code. This is the function of the Romberg integration. This is the refinement loop of the Romberg integration. And this is the Richardson formula and the convergence check where we need to check its convergence. And this is the table for the Romberg extrapolation. Okay, let's try to run the code. We need to input one, or the topic 5 is 1. Input 1 and enter your equation, which is the 1 over x. And we need to enter the lower limit. As I can remember, the lower limit is 1 and the upper is 2. So as you can see, this is the table for here. And this is the integral, which is the like this 0.69315. And the total refinement level of iteration is 6. We need to continue for the trigonometric equation, which is sine x. Lower limit is 0 and upper is 1. So you can see this is there on the table. And the integral is 0.4597 and the total refinement levels or iteration is 5. Okay. The last but not the least topic is the CDD plus Richardson extrapolation. Richardson extrapolation is a powerful numerical technique used to improve the accuracy of derivative estimates obtained via the central divided difference or CDD method. It works by taking a sequence of CDD estimates calculated increasingly smaller step sizes. By combining these estimates through a weighted average, the method systematically cancels out the leading errors terms, specifically the zero H word terms. This allows you to achieve the high order precision moving on from zero H squared to OH4 and beyond, with significantly less computational effort done simply using an extremely small step sizes. So as you can see, this is the formula of the CDD, where the H is the step size, F times X plus H minus F times X minus H. So as you can see, CVD is fast and future measure. And this is the Richardson recursive formula. Okay. The C, the extrapolation table. So this is the extrapolation table. And this one is the example problem for polynomial. And this one is a sample problem for the trigonometry. Okay, let's watch the video. As you can see, this is the Richardson function. This is the Richardson or CDD formula and logic. And this one is the Richardson formula. Yeah. And this is the derivation 1 and derivation 2. And this is the Richardson formula. Okay. So as you can see, this is the formatting output. Okay, let's try. Okay. So 2 for the topic 10 or the Richardson extrapolation. Let's put the value or the equation. As you can see, this is the answer. Using Richardson extrapolation is 0.5 for ln x. Okay, next is for the polynomial. So you can see we need to type the polynomial x cubed plus 2x squared. So at which x is equals to 2 and h is equals to 0.5. So d1 is equals to 20.25, d2 is 20.0625. And the first derivative of x is equals to 2 using Richardson extrapolation is 20. So that's all. Thank you for listening.